Hi, everybody. Let's do some notes on how you can tell how a parent graph has been transformed. This is only going to make sense if the transformation involves an integer. So if it's been dilated by an integer or if it's been translated by an integer. That said, the process is hopefully going to be fairly straightforward. These are all of the parent families, and you can see there are some reference points that you know. And if you look at two reference points, they often form a triangle that goes over one and up one. You can see that in all of these, except for this one. So the process is, first decide what family it is. This one is a square root graph. You would then decide whether it's been reflected. And you can do that by looking at the direction this one is facing and moving and comparing it to the original. So here we see it's kind of going up and right, and the original is going kind of up and right. So we know it hasn't been reflected at all. However, it has been translated and scaled. So if I choose a reference point like the end point here, the untransformed function is at 0, 0. This one I see has been shifted left by 5 and up by 2. So we could write just that much. Left by 5 would be x plus 5 on the inside because we're affecting x coordinates. Up by 2 would be plus 2 on the outside because we're affecting y coordinates. And on the outside of the function is where you have the y coordinates. Okay, last bit, it has been vertically stretched by a whole lot. So you have to, so if this was the reference point that used to be at the origin, it used to be I go over 1 and up 1. That was for the undilated function. Here, if I go over 1, we have to see how far do you have to go before I get to another integer coordinate. And so here I can see I went over 1, but up 1, 2, 3, 4, 5. So that means it's been vertically dilated by a factor of 5. So there we go. Let's try another one. This one looks like a cubic, except you can see that for the cubic, if I go to the right, it goes up. Whereas here, when I go to the right, it goes down. So you could think about this as having been vertically reflected. So this part flips upside down. That fits. Or you could also think about it as being horizontally reflected. If you imagine this point reflects over that way, you would still have this shape. So you could do either one you want. First, let's write the translations. So the reference point that used to be at the origin has been shifted left by 5 and down by 1. So I've got a cubic. Left by 5 would be plus 5 on the inside. Down by 1 would be minus 1 on the outside. If I'm going to vertically reflect it, I'll put a negative sign on the outside of the function because that's going to affect y values, which is going to move them to vertically reflect them. And then the last thing is same as we did before. Over 1, up 1 has become over 1, down 1, 2, 3, 4, it looks like. We already got the down part with the reflection, but we still need to stretch it by a factor of 4. So here I'm going to turn the negative sign into a 4 and add a new negative sign out there. And that will be a good equation for us. Let's do a last one with exponentials. So for exponentials, depending on what the base of the exponential is, it's going the sort of growth triangles you see here is going to grow by a different amount. So here you see over 1 up 1, over 1 up 2, over 1 up 4. And so you can see the growth triangle, or like the growth here, is always 1 less than the base of the exponent. What are we going to do? So let's do the same process. The first step is spotting what integer coordinates does this go through. Let's try and find where the triangle ended up, because that'll help us think about how the triangle was transformed. Okay, so I found my triangle. I see that because it's over 1 and then change in 2, that would be like a 3 to the x kind of equation. Except that this point, the reference point that used to be at 0, 1, has now moved left by 5 and down by... Oh, no, wait, sorry, where were we? So it used to be up here. So it's been moved left by 5 and down by, it looks like 7. So let's start writing it. So left by 7 would be x plus 7. Down, no, sorry, it was by 5. And then down by 7 would be minus 7. So that covers it. Let's look for reflections. So an ordinary 3 to the x graph looks like this. You can see that the long horizontal tail goes out to the left. This long horizontal tail goes out to the right. So I know it's been horizontally reflected. So I can horizontally reflect on the inside like this. I also see that in the original untransformed one, the side that is the opposite of the long horizontal tail is increasing very rapidly. Whereas here, if I look across from the horizontal tail, I am decreasing very rapidly. So that tells me that it's been reflected vertically. What used to be going up is now pointed down. So if I'm going to reflect it vertically, I'll put another negative sign on the outside there. Quick interlude. If you want to vertically reflect something, a second ago I just put the negative sign in front of the family, but that doesn't include this shift amount. Was that what I wanted to do? Or did I actually want to put parentheses around everything and vertically reflect everything? Well, it depends on what you're trying to do. So let's build it up one step at a time. If I've just got opposite x squared looks like the parabola, this would flip the parabola upside down. Then so once I've got that, if I add 5 on the outside, that takes my upside down parabola and shifts every single y coordinate up by 5. So that gives me an upside down parabola whose vertex is now at 0, 5. So the way to think about this is when you put the negative sign attached to the x squared, it didn't affect the plus 5. It's like I flipped the parabola upside down sort of at its own vertex, and then I shifted it up. This one, I mean, you could imagine distributing the negative sign in. So this would be the same as an upside down parabola minus 5. But let's think about how that makes sense. If I started off with just x squared plus 5 with no negative sign, that would be an upshifted parabola like this. Then if I wrap the whole thing in parentheses and add a negative sign, what I'm doing is I'm taking every single y coordinate here and I'm making it negative. And so that's going to take every single y coordinate and flip it across the x-axis. So that's going to give me this parabola that's upside down, but the whole thing's been flipped across the axis. So now the vertex is at 0, negative 5. And that's consistent with what we see up here if you distributed the negative sign. We've got upside down parabola shifted down by 5. So the big takeaway is, well, the big takeaway is really this thinking process. Like, if you're not sure, think, okay, what if I don't have the parenthesis? What does my graph look like? And then what exactly is getting negated? Like, which specific y values are getting negated? Are we flipping the y values before we add the 5? Or are we flipping the y values after we add the 5? And you can sort of visualize the transformations that way. Okay. Last bit was lines. This sort of doesn't really fit in this section, but I didn't have another place to put it. A lot of people are not in the habit of using the point slope version of the line, but it's a really, really nice form for the line to be in. So let's pretend I'm going from 5, 7 over to 10, 6. What you'll do is you'll figure out what's the slope. So what's that change in y over change in x, rise over run. Usually we use m to designate the slope. So the change in y would be 7 down to 6. So that would be minus 1. The change in x would be from 5 up to 10. So that would be 5. So that's a slope of 1/5. So the point slope form of the line is y. And then here you've got, let's fill in the bubbles, and then I'll tell you what the bubbles represent. Okay, so you have the slope. And then inside parentheses, you have x minus any x coordinates that's on the curve, the line. And then you have plus on the outside any y coordinate that's on the line. So here I could just use 10 as my x coordinate, 6 as my y coordinate, slope of negative 1/5. And so that gives me y equals negative 1/5 times x minus 10 plus 6. It would also work to say y equals negative 1/5 times x minus 5 plus 7. So it's a convenient form because you don't have to solve for b. You will use it a lot in calculus when you have to build lines that touch particular points where you know their slope. But that's it. You just know a point and a slope. Okay, hope this was helpful.